One of the most important concepts that you're ever going to discuss in organic chemistry is this concept of resonance. In this section of the course, the content is outlined on this slide, and we are going to be utilizing what we refer to as a flipped classroom approach, where I expect you to go through this section and the movie that is associated with it thoroughly before we actually come to the lecture. And then once we come to the lecture, we will discuss and work problems face to face. So the content is outlined in terms of writing the resonance structures correctly and understanding the stability that is associated with resonance structures. And by the end of this section of the course, I expect you to be able to do the following things, including predict stability of resonance forms relative one to another, and of course make an inference about the system. So far in this course, we have dealt quite comprehensively with how to represent molecular structures. We've dealt with KQLA, and my favorite, of course, would be bond line notation. But there are certain molecules in which there really is no one good way to represent them accurately. So let's start by taking a look at nitromethane, shown here. And I'll bring my laser pointer up in a second. So shown right here as CH3NO2. And you will notice that there really is two good ways in which I could represent nitromethane. So it could be represented with a double bond between the central nitrogen and the lower oxygen, or in the other option, it could be between the central nitrogen again and the uppermost oxygen. So the question is, where is the double bond? Well, both structures, both forms as I'll call it, really are quite valid. And is this the only situation where we get such an occurrence? Well, how about if we look at the structure for benzene? So C6H6. Once again, is the more accurate way to draw our benzene ring with double bonds shown on the left form or on the right form? Well, there really is no good single representation in either case. Both are just as valid. But these structures are actually referred to as resonance forms, and they clearly appear to differ only in the placement of their electrons or their lone pairs. So you can clearly see that with respect to the pi electrons that make up this double bond, these are definitely in a different position, or so it would appear, than the ones on this structure. Likewise, in my resonance forms for benzene, you would notice that those double bonds, and I'm doing air quotes right as I'm speaking, appear to have different positions. So those are our resonance forms. It also turns out that when we represent those, or when we're drawing those resonance forms, we tend to draw a double-headed arrow between those resonance forms. Now I need to stress at this point, this double-headed arrow is not the same as an equilibrium arrow. The electrons are not thought to be moving back and forth fundamentally. But the question is, what is the real structure? If they're really not moving back and forth, then what really is the structure? Well, if we take a look at experimentally obtained data, we actually observe that, and we saw this in class earlier, a double bond has a different bond length than a single bond. Single bonds are by far longer than double bonds. Well, one would have expected then that in benzene we would have alternating double and single bonds. In other words, there would be a long single bond, a short double bond, a long single bond right around the ring. That does not turn out to be the case. Instead, we have one bond length right around the ring. And likewise, in the case of nitromethane, you also see, or better yet, you don't see a clear single bond length, longer nitrogen-oxygen single bond, and a shorter nitrogen-oxygen double bond. But instead, you see one bond length for both nitrogen-oxygen bonds. So what is the real structure? Well, the real structure really is a hybrid. And all of the bond lengths are the same. So the best way to represent this hybrid, you'll notice, is with some dotted lines, signifying that really and truly the nitrogen-oxygen bond length is really half between a double and a single. I like to call it a bond and a half length. Likewise, in benzene, the best representation is to have it drawn with a ring, showing that there isn't double and single alternation, but instead it is one bond length, bond and a half, we would like to call it. So the electrons are not alternating between one position and another position. They really are spread or delocalized either around the entire ring or over 3 atoms in the case of nitromethane. The representations, however, are our only way of demonstrating the movement of electrons. But they're really not moving. But the only way we can show that delocalization is to show them in different positions, almost like a snapshot. But we know that's not accurate. We know that the reality is they are smeared, delocalized. Once again, the brace is giving trouble when I'm speaking. Now, to understand that delocalization, understand the movement, we have to explain our curved arrow notation. Now, some of this you would have met before, but for those of you who don't have a full understanding of this notation, let's take you from first principles. So I think we already know, everyone should know, that when we see a line that represents 2 electrons being shared, and we've even seen cases where they're not being shared perfectly equal. And that's because, of course, as a result of electronegativity differences. But when it comes to our arrow notation, that arrow notation, if it has just one head, represents just a single electron moving. While if we have a double-headed arrow, that represents 2 electrons moving. Electrons always move from a source, always at the tail, to a sink, the head. So in the case of a single-headed arrow, we're saying the source of one electron is the tail, and the head is where it is moving to, in other words, the sink. So the tail is the source, and the head is the sink. So if you think of it in terms of electrophilicity and nucleophilicity, we would say the source of electrons is usually the nucleophilic portion, and the sink would be the electrophilic portion. So the source would be either lone pairs, we'll see, or negative charges, and of course multiple bonds, and of course the sink would be a region that is lacking electrons, such as a positively charged center. So just to show that represented even more thoroughly, our sources are multiple bonds, lone pairs, and single unshared electrons, so radicals. And of course our sinks are those regions of positivity. In some cases it's an electronegative element because we know those elements can take more electrons. And of course there are some atoms with an open shell, and we see sometimes sulfur and phosphorus falling into that category. So our electrons move from source to sink. That means that we can never push from a positive charge, because a positive charge is a sink, it's a hole, there is no electrons, or there are no electrons in that position. So some examples just to show you, and for you guys who have printed your notes, feel free to annotate your notes now according to what you see. So the source, of course, would be our oxygen with additional or extra lone pairs and therefore carrying a negative charge. And remember, we've worked through formal charges in our first tutorial. And so if we were going to best represent how the electrons are moving, in my air quotes, between one structure and another structure, now let me reiterate, there is no one structure and another structure. The reality is that the molecule is the combined hybrid, but for purposes of illustrating, organic chemists have to show a movement. And so we're saying that the electron should be pushing from or moving from a source on the oxygen to a sink. But rather than just pushing to the positive carbon, we're really trying to say that we're moving our electrons, or our electrons are not just localized on the oxygen, but they're really sharing between the oxygen and the carbon. And so you will see that I haven't pushed directly to the carbon, I have more accurately pushed to share. So I've pushed to the middle of the bond. So from the oxygen's negative charge, or the lone pairs, which become a negative charge or confer that negative charge, to the actual middle of the single bond, which is now going to become a double bond. Now let's watch the charges. If the oxygen had extra electrons, you would remember that that means it carried a negative charge, and my carbon was lacking, and therefore it carried a positive. When I share those electrons now, more accurately, then now we're saying that oxygen has a perfect octet, so it has become neutral, so it has gone from negative to neutral, and our carbon that was lacking has become whole, so that has gone from carbon being positive to neutral. Let's give you another scenario and see if you can work ahead of me. Where's the source? So in this molecule, our source would be, remember the sources were listed here? So this source would be the lone pairs on the nitrogen, and the sink would obviously be the carbon with the positive charge. So one best way to represent it would be to use the lone pairs as our source, and our arrow is going to be pushed once again from those lone pairs. But once again, we want to represent sharing between carbon and nitrogen, so I push from the source, nitrogen, to the middle of the bond. Now let's watch the charges. Let's see that once again, nitrogen was neutral, so it was perfect, for lack of a better word, a happy nitrogen. It carried 3 bonds, and a lone pair was neutral. But once it gave up those electrons, it suddenly became lacking. Carbon, on the other hand, was lacking initially, but you gave it electrons, so now that is neutral. Now, did you actually notice something special about these charges, or those structures, or those forms, or those examples? Look at the overall charge in both of the resonance forms. So let's take a look at these two. Did you notice that the overall charge of the first resonance form was neutral, negative and positive, neutral overall? And did you also notice that the second structure was neutral overall? How about the second example? The second example had a positive charge overall, and did you notice that it still maintains that positive charge in the second form? And we're going to come back to this point, but overall, when we're drawing resonance structures, we must conserve charges. So if it is neutral overall, it must stay neutral. If it is positive, it must stay positive, etc. And oftentimes, this is a way of double checking that we've drawn accurate resonance forms. Now, later on in this course, we will see that this same arrow pushing notation can be extended to our reaction mechanisms. So while this is not resonance, you will note that I did demonstrate heterolysis. So in this case, we're saying all of B, or B, gets all of the electrons. And so in this case, you'll notice that B became negatively charged and A was lacking. While if I push in the opposite direction, I hope you'll notice that that means A is negatively charged. It has all of the electrons, and B is lacking. Now this isn't resonance, but I'm just trying to show you the analysis to what we will see later in reaction mechanisms. So that is heterolysis, an all or nothing proposition. Homolysis we've also seen possibly in your previous work or your previous chemistry tuition. And you'll notice in this case, you're actually giving each of A and B 1 electron. So watch the head of the arrows that I use here. So in this case, you'll notice that it is a single head. So this is saying B gets 1 electron, A gets 1 electron, and in this case, you're not forming ions anymore, but you're forming radicals. But we will see heterolysis and homolysis when we do reaction mechanisms in detail. But the concept of pushing arrows is the same as what you see for resonance. So there are some rules that we need to follow, and some of them I've mentioned in previous slides. So I've stressed before, those individual representations, those word resonance forms, are literally just representations that the organic chemists use, but we know they are imaginary. Neither or any of them, because sometimes they are more than the two, even though those are the examples I showed you previously, they're all imaginary. The real structure is the hybrid. We also mentioned before that the forms should differ only in their placement of non-bonding electrons or pi electrons. You shouldn't be moving atoms. Resonance forms don't move atoms, just those pi electrons, those double bond electrons, those lone pairs. Each of those resonance forms must be valid, so you'll see that I keep stressing that the charges need to be placed so that we maintain valid Lewis structures. And we'll stress this more than now that we need to follow the octet rule. Which one is more stable? Well, the real structure is the hybrid, so the hybrid is going to be more stable than any one of the individual resonance forms. And that makes sense because the hybrid is the real structure. But even when we draw multiple resonance forms or multiple resonance structures, they don't tend to often be equivalent. Sometimes they are, and sometimes they aren't. And we're going to come across rules for assessing stability of our resonance forms. The most stable resonance form is the one that is going to contribute most to the hybrid. I like to say that if you have multiple resonance forms and one is more stable than the others, the hybrid will most look like that form. So it's a bigger contribution if that particular resonance form is more stable. And we've talked already about stability conforming or aligning with low energy. So just to show you what I'm speaking about when I mention those rules, so here's my nice scenario, kind of similar to what we saw before. And we've already seen that we can show the representations or the transformation from one resonance form to the other by just showing this movement of electrons. So source to sink, giving us the same overall charge. And you'll notice once again I have that double-headed arrow. It's not equilibrium. And I even have some lovely square brackets implying that those relate to my hybrid. These are the resonance forms for my hybrid. What is the real hybrid? The real hybrid says that that electron density is spread over the carbon and the nitrogen. And so while each of our resonance forms can carry a positive charge, as shown before, my combined hybrid, you'll see, will carry partial positive charges on both the carbon and the nitrogen. So which one is the most stable of the three? Well, of course, it's the hybrid because the hybrid is the true structure. But which one of my two resonance forms is the more stable? And the reality is it is the second one. This one is considered the more stable. This is considered the major contributor. So what does that mean? It means my hybrid will most look like this. The less stable, of course, would be the other one. So how do we predict the relative stabilities? How did I come up with the fact that this was more stable than that? Just out of thin air? Absolutely not. Of course, we have rules for that. So how do we actually assess the importance of each of the resonance forms or each of the resonance structures? And we're going to start by doing this by example. So let's take a look at this particular resonance form shown on the left. And I'm first going to ask, how would we transform this into the resonance form shown on the right? So where's the source? Where's the sink? So it turns out in this example that we can clearly see the sink, the positive charge. But the source, there are no lone pairs, at least not on the carbon. And we can't be pushing from these lone pairs because that oxygen also is the sink. So that's out of the question. So we're stuck with the source being the multiple bond, the triple. And if you notice the transformation, you'll notice I'm moving from a triple bond to a double bond. and we're moving from having a positive charge on the oxygen to a positive charge on the carbon. An additional lone pair is also going on the oxygen, so we appear to be doing this movement. So the source is the carbon, is the triple bond, and that is being pushed onto the oxygen. And so in terms of our overall charges, you'll notice once again, positive charge overall, oxygen was lacking, was given electrons, now it is neutral. Carbon was neutral and the electrons were taken away from carbon, and therefore the carbon is now lacking. So overall positive, and the movement is source, triple bond to sink, oxygen. But which of the two of these is the more contributing? So for that, the first rule comes into play. And the first rule says that the structures which maintain a full octet, especially for all of the second period atoms, is more contributing. I carry this a step further and I say, is carbon happy? So in this case, you'll notice that carbon is carrying 4 bonds, so a very happy carbon. And in this structure, you'll notice that the carbon is carrying 3 bonds and a positive charge. So in this case, the major contributor is the first form. How about the second example? So here's the second example, and remember I told you there are 3 fundamental rules, even though they often appear to be overlapping quite significantly. So let's look at the 2 resonance forms. I think that we can right away see that it's overall neutral in one and overall neutral in the second. So we've conserved charges, so that's okay. So how do we show or represent the transformation of one resonance form to the other? So where's the source, where's the sink? So you'll notice that there's a single bond and a triple bond and 1 lone pair. And you'll notice in this case we have a double bond, and 2 lone pairs. So if you assess this correctly, you would have noticed that our source was our first nitrogen and our sink ended up being the second nitrogen. But notice that if we had only stopped after 1 arrow, and I'm putting my pointer to block that second arrow out. If we had stopped right after putting our 1 arrow, do you notice that that carbon, that central carbon, would have had 5 bonds, which we know is a fundamental no-no? So in other words, we have to make a bond and we need to break a bond. So we have nitrogen has lost electrons, this first nitrogen, and has become positive, lacking. We've made a double because we've pushed from the source to the middle of the bond, so lone pairs to the middle of the bond, and we've pushed from the middle of the bond to the nitrogen to imply movement from a triple to a double, and the nitrogen suddenly got an additional lone pair. So nitrogen at the end went from neutral to negative, and the first nitrogen went from neutral to positive. But overall, we're carrying the same neutral charge on the entire resonance form. So what's the rule? Which of the 2 of these forms is going to be more contributing? Well, it turns out that the minimum, or the form that demonstrates the minimum charge separation, is the one that is assessed more contributing. In other words, yes, it is overall neutral, but there is no separation of charges. Yes, it is overall neutral, but we do have separation of charges. So in other words, the first form is the major contributor. How about a second example? And let's see if we can denote the arrow pushing notation. So for that, you notice once again we have neutral oxygens, positive and negative. So where's the source? And we can mirror what we're seeing in terms of the change. And we'll notice that this oxygen is our source, so we've made a double. We've gone from a single to double, and we've gone from a double to a single. Once again, why 2 arrows and not 1? Because if I block the second arrow, then I hope you would notice there'd be a double bond here and a double bond here. So this carbon would have 5 bonds to it, which of course is a no-no. So we're making a bond and breaking a bond. Overall charge neutral in both. But in terms of the changes that we see, you'll notice that neutral oxygen lost electrons and became positive. and neutral oxygen gained electrons, and so it became negative. So which of the two forms is more contributed? Of course, if you determined that the first one was because it had no separation of charge, you would be totally correct. How about a third example? And we might very well see some overlap right here. But in the two resonance forms, I think we can see the conservation of charges, so overall neutral in both. But we can clearly see that there is a difference in the representation. So how do we get from our first form to our second form? And so you'll notice, let's start with the nitrogen. You'll notice that this is two lone pairs, a negative charge. And over here, our terminal nitrogen has just one lone pair and a triple bond and no charge. So it would appear as if that is our source. And so we're once again making a bond and breaking a bond. But I want you to focus on the central nitrogen. So this central nitrogen had 4 bonds, no lone pairs, positive charge. But once we've made our what appears, and once again I can say this with air quotes, as a movement, you'll notice that central nitrogen still has 4 bonds, and so it should still carry a positive charge. So nothing changed, not overall. But what did change in the representation is that we went from the nitrogen on the end, the terminal nitrogen, being in excess of electrons, to the carbon being in excess of electrons. So our source was this nitrogen and our sink was the carbon. So which of the two forms is more contributing? Well, here's where I said we might very well get some overlap between the first rule and this rule. But this rule says sometimes you can't help it. You have to show complete octet compounds, or atoms I should say, with complete octets, but you have to show charge separation. In those cases, the negative charges are more stable on the more negative or the more electronegative atom. But here's where I said there's some overlap, because if I refer back to what I interpreted as rule 1, I said make carbon happy. And so from the two of these forms, this is the form where carbon is happy. One could also argue that as the rule is written, the more electronegative element carried the negative charge versus carbon, which is of course less electronegative than nitrogen. So that's the major contributor. And in my last example says, well, let's look at these two resonance forms. And once again, you should be able to see that we have a source of electrons on the far oxygen, the only oxygen. And then once again, it ends up showing a representation where this carbon carries a negative charge. So, which is the source? Oxygen. Which is the sink? Carbon. Overall charge of both resonance forms is the same, neutral. So our arrow pushing should once again have 2 arrows. And even though this, it doesn't look like it right this minute, that should be pushing from the lone pairs to the middle of the bond. And so make it so. While the second arrow should be pushing from the triple bond to the carbon itself. So which of these two forms is the more contributed? Well, of course, that would be the first one, because carbon is happy. That's rule 1. And then, of course, the more electronegative oxygen is carrying the negative charge, rather than the carbon, of course, which is unhappy, is carrying a negative charge as well. Now, even though in all of my examples, the first structure ended up being the major contributor, sheer coincidence. So notice that it does not always work out that way. In fact, it almost never works out that way. So now that we have assessed stability of our actual resonance forms, we're working our way towards actually drawing them. But before I go a step further, and you'll watch my slide show the words getting bigger, I need to stress the commandments. Very simple. Resonance is not the same as a reaction mechanism. And maybe that doesn't make a lot of sense to you right this minute, but it will in a few seconds. Because in a mechanism, you are going to be breaking single bonds. But in resonance, that's a big no-no. So thou shalt not break a single bond. Never do it. Make sure that you do not violate the octet rule, and never ever push from a positive charge. Remember, a positive charge is, I like to call it, a hole. And so you can't move a hole. It's physically impossible. What you can do is move, and I use the analogy of a hole in the ground that a gardener had. So if there's a hole and the gardener put it in the wrong place, and you came home and you said, hey, I don't need it in that position, how does the gardener move the hole? The gardener cannot physically move this hole into another space. What the gardener has to do is move dirt from the new position into the hole, and in so doing, create a new hole. So in other words, you can't move a positive charge by just moving it. Instead, what you're doing is moving the electrons into where the positive charge is, in other words, the dirt, and in so doing, you're creating a new hole, a new positive charge in a different position. But you're not technically moving the positive charge, you're moving the electrons and creating a new positive charge. So to draw our resonance structures, the best way I can show you is to show you some patterns that we're going to see when we practice in the lecture. So the first pattern that you are going to encounter is a pi bond next to a positive charge. And that has a special name. So this is referred to as a allelic. My handwriting is not very good, but worth a chuckle. But that should say A-L-L-Y-L-I-C. So allelic. And so when it comes to a situation or an orientation in which you see a positive charge next to a pi bond or a double bond, then that is referred to as an allelic carbocation. So the allelic position is next to or on the carbon next to the double bond. That's the allelic position, on the carbon next to the double bond. So there's a particular pattern that we tend to see when we see that allelic carbocation. Now remember, push from source to sink. So for those, we can show that the source, the nearest source, has to be the double bond. Because remember, we said there are three sources: lone pairs, negative charges, or multiple bonds. So to show the representation, or the difference in the representation between the first form and the second form, it would very well appear as if my positive charge moved. But we just said positive charges don't move. Electrons move. And so to do this, or to show this, you will notice that we're saying we're going to push from source, middle of the double, to sink, middle of the single. Why middle? Because remember, we want to show that we're going to share those electrons between these two carbons. Now I said next to. What does next to mean? Next to means we have a single bond separating those two things I mentioned. So next to meaning I have a single bond between my positive and my multiple bond. So overall, what have I done? I have moved the electrons from sharing between this carbon and this carbon, and I'm now sharing between this carbon and this carbon. I like to say this central carbon was calling all the shots, was sharing the electrons with his friend. Said, no, not going to share with you anymore. I'm going to share with him. But you'll notice that in both cases, this central carbon was still part of the double bond. So there it is again, still part of the double bond. But friend 1 should now be lacking. Carbon in this position should be lacking. But the carbon on the end was just given electrons, so once again that should have now perfect or happy orientation, and as a result that is neutral. Overall, two structures still positive. But there's another source on the other side. So how do we show that potential movement or that involvement? In that case, once again, source to sink. So we have another allelic situation over here. Still allelic on the carbon next to the double bond. And notice you're still pushing from source to sink, middle of the bond to middle of the bond, and as a result, you get this orientation. So this carbon now was calling all of the shots, took the electrons away from this carbon. You're saying the electrons will now be shared with this carbon, so that carbon in the middle still has or still is part of the double bond. But the carbon on the end is now lacking. So what would be the hybrid? The hybrid literally would be the molecule that now has the delocalization or the spreading of the electron density over multiple carbon atoms, shown here, and that positive charge also being possible on multiple atoms. In other words, you'll tend to see a dotted line right across to the end and a positive charge kind of hovering in the middle to show that it's actually possible, or it is actually equally likely over all of the atoms. So that's one pattern that we see. This second pattern we've actually seen before, and this one has a lone pair next to a positive charge. And in this case, the source once again would be the nitrogen lone pairs. And so we would once again show pushing from source to sink. So from the lone pairs to the middle of the bond, overall charge is staying the same, I should say. But in this case, once again, carbon became happy and nitrogen is now lacking. So that orientation you often see as well. We often also see another pattern where we see once again now lone pairs next to a multiple bond. This looks actually like if it is more than one source. So one potential source, of course, could have been the multiple bond, and another source, of course, could have been the lone pair. And I'm going to stress this in lectures because in situations like this, the lone pair often wins. In most cases, it's the lone pair that is allocated as the source. And so in that case, you'll notice that we need two arrows again. And in the previous two examples, you will notice that we only use one arrow. And I'll make or emphasize that point as well in the lectures. But in cases where there is a positive charge that you are pushing towards, we tend to just use one arrow, saying source to sink. But in the cases where the sink isn't as obvious, there's no positive charge, we know that if we had only pushed with one arrow from our initial source, then this central carbon would have had 5 bonds. Why? Because what we do know, and I'm going to bring up my pen, and you know my pen is always a little problematic when I'm trying to draw him in. But please remember that there is, boy, that was handy. There's a hydrogen shown right here. So if I pushed in such a way that there was only one arrow being used, then you'll notice that there would be 5 bonds to this carbon, which of course is a number. So you're making a bond and breaking it up, which means now that the oxygen that went from neutral is now lacking, and the carbon on the end that was neutral now has electrons in excess. Overall neutral, charge conservation. How about this scenario? And this scenario shows now a pi bond between two atoms, one of which is more electronegative. And so in this case, you'd notice you have carbon and oxygen clearly being more electronegative. So if you want to show this representation quite slowly, your first movement would be pushing from the oxygen onto the from the carbon onto the oxygen. Which means therefore that our oxygen is going to be in excess, so it's going to move from neutral to negative, and our carbon is now going to go from neutral to positive. Overall conservation of charges, neutral. But isn't there another source nearby? So while the first one follows my new pattern, the second one kind of more represents this pattern, the lone pair next to a positive charge. And so for that, you'll notice that we're pushing from the source, I'm going to make that mistake. From the source, the actual nitrogen with lone pairs, the sink, which of course would be the carbon with the positive. But of course we show it as sharing. So source lone pairs to the middle of the bond sharing. Once again, overall, neutral, overall, neutral, overall, neutral. And our final pattern is one that most of you may be very well more familiar with, and that is pi bonds going all the way around the ring. For that scenario, you'll notice that once again we're going to be using multiple arrows in the same structure. So how about this one? So this is showing that we're actually showing difference in the depiction between the first form and the second form. And then we know that it is possible to involve our second benzene ring, in which case you get movement as shown here. Now there are no separation of charges. It's neutral in all three species. And this molecule you'll actually see in your actual lab course if you're doing 1125, in which case this compound is called naphthalene. So that is our probably most familiar way of recognizing a compound, but the others we will see over and over and over and over again. All right. So why do we even go through this entire process of dealing with resonance structures? Well, we already mentioned why, and that is we have structures for which there's no one good single representation. But there's something that is very significant for organic chemistry, which comes along with this concept of resonance, and that is resonance stability. So the ability to delocalize charges or to delocalize electrons confers on molecules stability. And that stability then is manifested in a number of other areas. So just to show you one example, let me take you through this particular case. Let's take a look at these two structures. Both are negatively charged compounds. The first one I refer to as phenoxide, and the second one is an alkoxide from a cyclohexanol. So A, phenoxide, and the second one, B, is what we refer to as an alkoxide from cyclohexanol. So really deprived from alcohols. So my question is quite simple. Which of these two ions do you think is more stable? And then we're going to figure out what does that stability tend to lead to, because that will feed into our next section on acidity and basicity. So which one is more stable and why? Well, it turns out that the first one, A, phenoxide, is clearly more stable. The why brings back in now our concept of resonance. So for phenoxide can be best represented as a number of resonance forms. In other words, phenoxide is not adequately represented as shown here. The hybrid instead is a delocalization of electrons right around the ring as my pointer is illustrating. So how do we show that representation or that difference in depiction? For that, you will notice a pattern that we saw before. So we have a negative charge or a source adjacent to or next to a multiple bond. So our source means that we're going to push from our oxygen. So we're going to make a bond, and we're going to break a bond, and we're going to stop on the carbon. So that means that now my oxygen becomes happy, went from negative to neutral. I've made a double, I've broken a double and made a single, and I've placed all of my additional electrons on this central carbon shown here. But that's not the only arrangement I see. Instead, I see another allylic arrangement. In other words, a negative charge on the carbon next to a double bond. So I can also enter into conjugation or enter into delocalization, or I can draw another resonance form. So once again, make a bond to the middle of the bond, break a bond from the middle of the bond to the carbon. That's going to once again make a new double. So you'll see my double. Everything else is being held constant, so this double bond is still there, those lone pairs are still here, this double bond is still here. But we have moved or shown an action that would appear to be a movement to give us a double here and a single here and a negative charge now at the bottom of the ring. Why is this negative? Because remember we have just given that carbon all of the electrons. But I get another allylic relationship. And so for that, I say once again, let's show movement of electrons make a bond, break a bond. And by breaking a bond, we're once again creating now a carbon with additional electrons, so it becomes negative. But we're taking away these electrons and sharing them, so you'll notice that we went from the electrons to the middle of the bond, from the middle of the bond to the carbon. And then finally, can we go once more? Another allylic relationship. So let's make another bond. Let's break our final bond, and our sink, of course, is the electronegative oxygen. What does this mean? This means that this negative charge is delocalized around the ring. And by delocalization, we have conferred stability. So we have a general form, a general saying. We're saying that in general, if you have a number of resonance structures, the more of them that we have, the greater the stabilization. In other words, we are delocalizing, smearing, spreading that charge over a number of resonance forms. This is good. That confers greater stability to the hydrogen. In addition, if we happen to have resonance structures that are equivalent, in other words, no one form is better than the other, then that confers more stabilization than if we have inequivalent ones or unequivalent ones. And so at this point, we end resonance. So in the lecture now, we're going to work through problems. We're going to look at bad pushing of atoms. We're going to look at how to push atoms, and we're going to get our resonance on. So thanks for listening.